This is Jack Jackson back with the second of a series of three videos going over some review problems for Unit 1 in Survey of Calculus. These problems also go over, this particular video goes over the problems related to basic concepts of a derivative. So this video is actually going to be placed in the second of my several units actually on calculus, whereas the first video in this series is placed in the first playlist, and then the third video will be placed in my third playlist for calculus. So anyway, here's the question. Complete the following table summarizing the meaning of the difference quotient, symmetric difference quotient, and derivative. When I get to a problem here, what I'd like you to do is to stop and work these yourself, and then come back and pause the question, pause the video, work the question, and then come back and check your answer. So in this column, answer these questions about the difference quotient. The middle column, the symmetric difference quotient, and the last one, the derivative. So we want the first row, we want the actual definition of the thing. So this is going to be an algebraic formula. Then the second row is going to be a geometric graphical representation. In other words, this is going to be a graph and a picture in this row. And then you're going to describe in words what's going on with this picture that's in the second row. They're going to describe it in words in the third row. And down here in the last row, you're going to give a physical or contextual interpretation of what these things mean. So this is this table right here, really I consider as one of the most core basic things in a basic calculus class, Calculus 1 or Survey of Calculus class, that you understand these basic concepts, because the difference quotient and symmetric difference quotient both lead to the derivative and lead to approximations and the definition of it. And a derivative is what we spend at least half of our time in Calculus 1 and Survey of Calculus on. So go ahead and work this out now. Press pause. Okay, so let's review this. Here are the actual definitions. Algebraically, the difference quotient is defined to be f of a plus h minus f of a over h. Here we're thinking of h as being delta x, some small change in x. A is a particular x value, so this is the derivative at a point. You could have also done this as an x instead of a, and then you're thinking of that as the derivative function, where we have this at different at a variable place. But if we're thinking of the derivative at a point, which is what I was thinking here, then we're talking about a specific value of a. And then this is a number. This is a difference quotient for a specific value of a specific function, a specific value of a, and a specific value of h. This is a number. We'll see that it's a number with a meaning, which we'll go over here in a second. Now, the symmetric difference quotient is similar. It's f of a plus h, but then it's minus f of a minus h, and it's divided by 2h. And we'll see in a minute that 2h is our delta x from our table or our graph. Now the derivative is just the difference quotient, then with the limit as h goes to 0, it's f of a plus h minus f of a over h, and take the limit as h goes to 0. It is true that if this derivative exists, then the limit as h goes to 0 of the symmetric difference quotient is the same thing, but the derivative is defined in terms of the difference quotient, in part because if f of a does not exist, we do not want the derivative to exist. Geometrically, here's what's going on. So we have some graph of a function, f of x, that's this blue graph here, and we have a point, this bright blue dot here, a f of a. So we're given some particular value of x called a, then we find the y f of a. So x is this, a is this x coordinate, the y coordinate down here is f of a, or this vertical distance with the appropriate positive or negative sign, is the f of a. Then we move over some distance h, so this red length right here is h, here I've made h positive, and we go to a new point, t, which is a plus h, nearby point, find f of that, so a plus h is a new x value, then f of a plus h is that new y value, so it's this vertical distance here, or this y coordinate, with the appropriate sign, of course. And so this gives you a nearby point, so a, f of a is one point on the graph, and then we have a nearby point, a plus h, comma, f of a plus h, and we find the slope of that slope between those 2 points, that is the slope of that secant line, that green secant line to the curve. So in words, the difference quotient is the slope of between 2 points on the curve, that is the slope of a secant line to the curve, where one of the points is this blue fixed point of interest. Symmetric difference quotient is very similar, except we don't use the blue point of interest. What we do is we go to the left and to the right h. So we go to the right h and again find this point a plus h, f of a plus h. Okay, but this time what we're going to do is also go to the left by the same amount to a minus h. So we have an x value of a, and then we have x values on both sides, a plus h and a minus h. Find the corresponding y's, f of a minus h and f of a plus h, and that basically defines 2 points, a minus h, comma f of a minus h, and a plus h, comma f of a plus h. Use those 2 points and find the slope of that orange secant line. And that gives you the symmetric difference quotient. Again, it's a number, but it's a number with a geometric meaning here. So the symmetric difference quotient is the slope between 2 points on the graph, again. And again, it's the slope of a secant line to the curve, but the difference between it and the difference quotient is the 2 points are equally to the right and left of the point that we're interested in. Now, when we take the limit as h goes to 0, in either case here, the blue point is fixed. Both the green point and the orange point are getting closer and closer to this blue point here, and both the green and orange tangent lines get closer and closer to this pink, green and orange secant lines get closer and closer to this pink tangent line. And so the derivative then is the slope of the graph at a single point of interest, something that doesn't really make sense with pre-calculus, but with calculus it makes sense. The slope of the graph at a single point of interest, in other words, the slope of the tangent line to the curve at that single point of interest, and that gives us a geometric meaning. Now, in a physical contextual situation, what we're talking about are rates of change. So slopes, of course, we know are rates of change. So the difference quotient and symmetric difference quotient are both average rates of change in the function over the interval. The difference is, of course, that the difference quotient, the interval, has one end of it being the point of interest, whereas the interval on the symmetric difference quotient goes on either side of the point of interest, either side x, y's, but not necessarily equally spaced y-y's. So horizontally symmetric. The derivative is the instantaneous rate of change in the function at a single point. Okay, so here's what about doing some approximations of it? So here is a table showing the price of gasoline on several different days in a certain year. And this is actually price in dollars per gallon. Okay. Well, it says of a gallon, so, okay. Okay, so what's the average rate of change from January 1st to March 1st? Well, notice from January 1st to March 1st is 2 months. So if we measure in months for our time, then we have delta. So if we measure in months, then we could let this be, say, 1, 2, 3, 4, or 0, 1, 2, 3. And we see a distance of 2 months there for delta x. And delta y is 3.21 minus 2.58 goes up $0.63, 63 cents. So the average rate of change then is $0.63 really per gallon per 2 month period. So that's $0.315 per gallon per month. What is the average rate of change in the price of gasoline from March 1 to April 1? Okay, so now we're using these 2 points to do a slope. Again, this is a difference in months of, well, this time just 1 month. And we do the final minus the initial here. So 2.96 minus 3.21 is negative 0.25, so it went down a quarter in that particular month. And so the average rate of change is negative $0.25 per 1 month is negative $0.25 per month. What's the best estimate of the instantaneous rate of change on March 1st? Well, again, we don't really know the instantaneous rate of change, but our best estimate when given a table like this is to use the symmetric difference quotient. So use that point and do the slope formula. Well, the delta x is February to March to April. That's 3 months. 2 months. February to March, March to April. That's 2 months. And we have 2.96 minus 2.63. And so you work that out, and it turns out to be $0.165 per month. It's our best estimate of the derivative. What about estimating the derivative from a graph? Okay, here we're given a graph. Approximate f prime at 1. Well, we find 1 here, and we look here. Well, the first thing I want to notice is that the function is decreasing there. So when I'm done, I should have a slope that's negative. Okay, some kind of negative slope. Okay, now you have to look carefully at the scale. Now what we're wanting to find is the slope of the tangent line. In theory, you could try to draw the tangent line and measure the slope, but in practice that doesn't work very well. So what you want to do is you want to do a symmetric difference quotient. So I just go one grid line to the left and to the right. If the grid lines are really widely spaced, you might go half a grid line, but I think one grid line will work well here. And then we know what the x's are. In this case, the scale is 0.1 each on the horizontal. So this is 0.1 here, and or 1.1 here, and 0.9 here. So it's 0.2 for delta x. We know that's exact. What we have to estimate from the graph is the y value. So we have to figure out a y value here at 1.1. And let's look at our scale. It's 4, 5, 6. So these are 1 each. So let's see, where am I again? I'm right here. That's between 5 and 6. So something between 5 and 6. Let's see, what did I estimate? I said 5.5. Looks like it's right about in the middle. Okay, how about this one here? This one here is between 6 and 7. It's close to 6.5. I want to say 6.4, I think. No, 6.5 is probably closer. Okay, and then we work that out. So 5.5 minus 6.5 is negative. So we have a negative slope, decreasing function. And the denominator is 0.2, and that works out to be negative 5. Okay, now if I ever ask you to do one of these on an exam, I'm going to allow a little bit, like if you'd have said 6.4 here or 6.6 instead of 6.5, it probably would have worked out close to this, and it would have been probably still would have given you credit for it. Number 11, the cost in dollars of producing X units of a certain commodity is given by this formula here, which I can put in my calculator. Find the average rate of change of C with respect to X when the production level goes from 100 to 105. Well, we're just doing the slope. That's a difference quotient if we're considering 100 our point of interest. A symmetric difference quotient if we're considering halfway between 100 and 105 as our point of interest. Or if 105 is our point of interest, it's a difference quotient. Okay, so anyway, it's a slope formula the way we go. So since I have this in as y1, I can just do parentheses y1 of 105 minus y1 of 100 in parentheses, divide by parentheses 105 minus 100. And that's 325. Let the calculator do the figuring out the things for me. So the average rate of change is the slope between the endpoints of the interval. Okay, and the average rate of change with respect to X when the production level goes from 100 to 105 for X is $325 per item. Notice that the units on this are your C units divided by your X units. X is just number of items. C is cost in dollars, so it's dollars per item. Do another one like that. How about the average rate of change from 100 to 101? Just go back and do second enter and change 105 to 101 here and here, and it works out to be 312.96. If we did this with smaller and smaller and smaller and smaller h's, we would come closer and closer and closer to the actual derivative. If we want to find the instantaneous rate of change, one way we could approximate it, rather than doing just difference quotients here, we could do symmetric difference quotients, and we could get that on the calculator by doing numerical derivative of y1 with respect to x at 100. Here's how we can do this on a TI Inspire. We can do the numerical derivative this way. We go to this one right here, this little button right here that has all these little symbols on it, and we select this one, get our cursor using our keypad on this symbol right here for derivative, hit enter, and this down here in this box is x, and we're taking the derivative of, again, if I have this in as y as f1, which is what would be on an Inspire, I can do that. Or if I don't, which I don't yet, I can actually put the formula in here. Where's my formula? There it is. All right. Okay, my formula. 5,000 plus 20x minus 0.05 x squared plus 0.01 x cubed. Okay, there it is. And then I want to say such that, so such that's a vertical line. See a vertical line right there? So it's blue, so I go control and equals, and then arrow over till I get the blue one. I can hit this button in the middle, it's one way, or the enter, and then say x equals, what was x equals? 100. Now I have the cast version, so if I hit enter, it's going to give me an exact value. But if you don't have the cast version, control, it'll be, when you hit enter, it'll be approximation there. If I in this case, that's exact. It is the exact value, 310. Now, if you have the newer version of the TI-84, it's going to look a lot like this this picture here. And let me see if I can paste that in there. Yeah, that's what it looks like on the Inspire. And like I said, it's very similar looking on the newer version of the TI-84. On the TI-84, let's see, I don't want it there. I want it down here somewhere. There you go. So on the TI-84, it's math 8 to get this numerical derivative either way. To get y1, you can hit the variables key, the ARS, right arrow to y variables, hit enter for function, and then hit enter for y1 if you've got it typed in y1. And if you have it on the 84, if you already have it in y1, instead of typing the formula right here, you would put, you could just put y1 if you want. But it looks very similar to this on the new version of the 84, which is basically Leibniz notation. So either way, what's it doing? It's actually doing a symmetric difference quotient. It defaults to be 0.001 on a TI-84. Here you can force, on the, with the older version here, you can force, or the math print turned off, you can force a smaller h, but we see there's no change. So in fact, that's actually an exact answer. Now, if you know derivative shortcut rules, then you can do this another way. So at first, actually at the place I'm putting this video in the playlist, we haven't gone over these yet, but later on we will. So derivative of constant 0, derivative of linear here is just the coefficient, and then we can use the power rule here. 2 times negative 0.05 is negative 0.1x to the first power, goes down 1. 3 times this is 0.03, and the power goes down 1 to second. And now we can just plug in the 100 in place of the x here, work this out on a calculator or by hand, either one, and it get 310, and so that is the exact value. So if you know the algebraic shortcut, derivative shortcut rules, you could do it this way, or you could just do it with a numerical derivative on a calculator that way. Either way, you get the same answer. Next, number 12. The daily cost of producing X ounces of gold from a gold mine is given C, which is some function f of x. What's meant by f of 400 equals 120? Be sure to use appropriate units throughout. Well, 400 is the x value, which is the ounces of gold. 120 is the f or c value, which is the cost, which in the United States would be dollars. So this says when we produce 400 ounces of gold, daily cost, so per day, then it's $120 for that day to produce it. So it costs $120 to extract 400 ounces of gold in a day. Is the derivative positive or negative? How do we know? Anytime we ask about whether the derivative is positive or negative, we're asking about whether the original function is increasing or decreasing. Well, anytime we talk about increasing or decreasing, we always increase the input. That is, we go left or right on the graph. The question is, does the y, or output, or in this case the c, does it go up or down? Well, if we increase the number of ounces of gold that we're extracting, then that's going to increase the cost. So c is an increasing cost of f, so therefore it must have a positive slope, it must have a positive derivative. So the sign of the derivative is positive. So that makes sense for this to be a positive 12 here. What is meant by f prime of 400 equals 12? Now be sure that you're careful and not confuse f of 400 and f prime of 400. These are two different functions. We have the original function up here, and down here now we have the derivative. So that's the slope here. So the slope of the original graph is 12 when x is 400. What does that mean in context? Okay. Well, in context, this should be some kind of rate of change, actually an instantaneous rate of change. And the units are always output units over input units. So they're going to be the units of f, or in this case, f is c. So cost, which that's dollars. And then we have the input is ounces. So when they are producing 400 ounces of gold each day, at that point, the instantaneous rate of change in the cost is $12 per ounce. So one of the things that would mean is adding 1 more ounce of daily production, particularly going for 400 to 401 ounces each day, will increase the cost by approximately $12. All right, here are 3 graphs. So the question is, one of these is a position graph, one is a velocity graph, and one is an acceleration graph for a particle moving on a straight line, a number line, let's say. First question is, which is which? Okay, well, there's some relationships here among these that we can see. First of all, we know that with the position, if we think of that as our base function, the derivative of position with respect to time is velocity. So velocity is the first derivative of the position. And then acceleration is the rate of change of the velocity. So that's the acceleration is the derivative of velocity with respect to time, which makes it the second derivative of the position with respect to time. So what we have here is we have a function, its first derivative, and its second derivative. So how can we tell which is which? Well, it turns out that this one right here, this red one that's going up and down and back up again, is the original position curve. Okay, and how can we see that? Well, if it's going up, the original function's going up, the derivative should be positive. So that makes this one the positive right here. That's the derivative. And where the original hits a maximum, the derivative is 0. So far it's making sense. Then as the original function decreases from here to here, the derivative will be negative, which is this. The original function hits a minimum where the derivative is 0, and then the original function increases here, meaning the derivative is positive. Furthermore, the original function is concave down here, and this is going to happen while the derivative is decreasing and the second derivative is negative. Where that second derivative hits 0, which turns out to be right at 2, the first derivative will be at a minimum here. We'll have a horizontal tangent line for sure. In this case, it's a minimum, local minimum. And that will be right there at x equals 2 is where the original function has an inflection point. And then it switches from concave down over here to the left, and to the right of that inflection point, the original function is concave up, which means the derivative is increasing and the second derivative is positive. So all those things kind of go together, so that should tell us which is which. When is the particle at the origin? The particle is at the origin when the position is 0. The position is the red one. This one is going up, down, up. So it's right here, negative 1.5 something. Let's see, these are 0.1 each. So I'm going to say negative 1.55 maybe. And then here's another place where it's at the origin here, 2.16 or something like that. And then over here, it's at the origin again at 5 point something, 5.38, something like that. Let's see what I said down here. Well, I just rounded off to the 10th. Negative 1.5, negative or positive 2.2, and 5.4. When is the particle to the right of the origin? The particle is to the right of origin when the position is positive. So between here and here, where this is positive above the x-axis, where the graph is above the x-axis, is when the particle is to the right of the origin. So that's between whatever I said that x is to whatever that x is. And then it's also positive over here. The original graph is above the x-axis over here, so that's another place. So from there on. So that turns out to be between negative 1.5 and 2.2, and then from 5.1 to infinity. Again, those are just kind of rounded off to the nearest tenth. When is it moving in the forward direction? Well, moving in the forward direction is increasing here for this one. And so it's moving in the forward direction when the velocity is positive. That's when the derivative is above the x-axis. So that's between, well, negative infinity, let's say, if it keeps going like that, to 0. And then from 4 to infinity are the places where the derivative is positive and the original function then is increasing. Okay, that's what I've said here. Of course, negative, it's moving in the negative direction in between 0 and 4. And it turns around going to the right to going to the left right here at this maximum. And it goes from going left to going right at this minimum. And those happen exactly when the derivative is 0, is when we have a local maximum on the original function. So those happen at x equals 0 and x equals 4. I think that was my next question. When is it changing direction? When is it increasing in velocity? Okay, so let's look back at the velocity curve. The velocity curve is the this parabola here, which I believe is purple on my screen. And so that is decreasing here and then increasing here, where the minimum happens, looks like right at 2. So I think the question was, when is the velocity increasing? That's going to be when this part over here, and notice that's exactly when the second derivative is positive, meaning the graph is above the x-axis. So from 2 to the right forever, it's increasing in velocity, greater than 2 specifically. Okay, continuing on. When is it at its minimum velocity? So that's going to be when the velocity is the furthest down. That's the purple one here, the parabola. That's the furthest down right here at x is 2. And that's going to happen when the second derivative is at a 0 and the original function is at an inflection point. That's the lowest the velocity is. Of course, the absolute value of the velocity is lowest at 0 right here and here, but the actual total value of the velocity is the furthest lowest, being a negative number right here. So its speed is 0 here and here, but the velocity is the lowest when x is 2. On this interval that is graphed, when is the x value going to be the smallest? No, when is that's not what I'm saying. When is it farthest from the origin? Okay, so that's when the absolute value is going to be, the distance from the origin is the absolute value of the, well, actually of the y value on the original position function. And if you look at the position function, I think you can tell, so the places we would want to look at are the local minimum here, the local maximum here, the endpoint here, and the endpoint here. If we assume this is the total interval, and we can see the furthest it gets away is up here when it's to the right by about 13. So it's about 13 units to the right. The lowest it gets on this interval is, well, not quite to -5, so less than 5 units to the left. So the farthest away from the origin is at the right end, which is whatever t value that is. This is the t-axis here. Looks like that's about 6.5 and about 13. So time ticks 6.5, it's 13 to the right. That's the farthest. When is the acceleration positive? The acceleration is the green one with the line, straight line. It's positive when it's to the right of 2. Notice that's also when the acceleration is positive is when the velocity is increasing and the position is concave up. So that's to the right of 2. T2 to infinity. All right, what about given a data right here? For volume as a function of time, explain in the context of the problem and give appropriate units. What's v of 26? What does it mean? Well, this is t and this is v, so you find t is 26 and we see that v is 225. So v of 26 equals 225, which means that at time t equals 26 minutes, the volume is 225 gallons. What's the best estimate of v prime of 26, and what does this mean? So this is your point of interest. Take the points on either side and do a slope formula, and that's a symmetric difference quotient. That's going to be our best estimate of the derivative there, which, by the way, turns out to be the same as if you just do a difference quotient of these two and average them, since the 26 is halfway between the 19 and the 33. In fact, I believe I've got this spaced where they're going up by 7s each time on the y, on the x, the t. So here, v prime of 26 then should be approximately 112 minus 450, that's delta y of negative 338, over 33 minus 19, that's a delta x or delta t of 14, and that is approximately negative 24.14 gallons per minute. I've rounded off to 2 decimal places there. So at t equals 26 minutes, the volume is decreasing at approximately 24.14 gallons per minute. So whatever this is the liquid maybe that's in it is draining out. And that's how fast it's going at that particular time. What's the best estimate of v double prime of 26? Estimate a second derivative from the table. Well, to do that, we first need some first derivatives. So what we'll do is we'll take these 2 points here at 19 and 26 for t, and this will give us an estimate of the derivative, say halfway between 19 and 26. And then we'll do the same thing here, use those two and do a slope. That'll give us an estimate of the derivative halfway between 26 and 33. So looking back at our table there, you see that 19 plus 26 divided by 2 is 22.5. That's halfway between 19 and 26. And then the derivative there is approximately 225 minus 450 over 26 minus 19. That's using these 2 points right here. And then doing the slope, and that turns out to be about negative 32. Well, it's negative 32 and 1/7. And then we do 26 plus 33 divided by 2 is about 29. It is exactly 29.5. That's halfway between these two t values. Use those 2 points and do a slope. And here it is worked out. And so now we have a table of t values and v prime of t. And notice halfway between these two, 22.5 plus 29.5 divided by 2 is in fact 26, where we want to look. And then we just do a symmetric difference quotient, that is, use the slope formula on those 2 points, and we get 16/7, or about 2.29 gallons per square minute. So notice the units of v prime of t will be the units of v over the units of t, so that's gallons over minutes, and the units of this is gallons per minute here. This is t is minutes. So now for the units of v double prime, it's gallons per minute divided by minutes again, which we can write as gallons per square minute. So it's gallons per minute per minute. So the fact that this is a positive number means the function is concave up and decreasing. So decreasing, concave up, means it was dropping faster before, more before and less later. So it's decreasing at a decreasing rate. Alright, so we'll pick up here on the next video to finish up the problems on this review set. And these last set of videos will actually be in my 3rd playlist online and for calculus, and they will involve using the derivative formula and using derivative shortcut formulas and some related things to that.